Yes. Yes. Okay. Spin is visible, right? To everyone? Okay. Thank you. Thank you. So today we are going to have a 2.5 hour session because of yesterday's network issue and all those kind of thing. So what I thought of is to cover some of the algorithms today. So where we exactly left tomorrow is we have seen so far whatever we have seen, just the relevant ones for today's classes. We have seen that what is a qubit, what is a quantum state, and how with respect to what is a quantum gates. There are basically a few types of quantum gates for like a single qubit gates as well as two qubit and multi-qubit gate. Two qubit is CNOT and C phase, multi-qubit is Toffoli. And of course, if I want, I can generate any of my multi-qubit gates if I want to, with like with respect to a single qubit and a two qubit gates that we can devise. Just like a say a four input and whether we can do it or not. Just in the similar logic, we can also think of building some more numbered multi-qubit gates with respect to the single qubit and two qubit gates. And followed by that, we have seen the basic construction of quantum circuit. It's basically a time diagram. That is why we had drawn a certain kind of vertical bars, plotted it like a T1, T2. That what happens with respect to that quantum state at time T1 or T2. Audio is okay or not? One just mentioned no audio. Okay, thank you, thank you. Please rejoin. Please rejoin. Money. So the thing is, we have seen that how the quantum state evolution takes place with respect to a particular time. So after T1, what will be the fate of the quantum state? After T2, what will be the fate of the quantum state with respect to all the individual qubits? So just put all those things in your mind. That all the lines are basically, they mean the qubit number 1, qubit number 2, qubit number 3, and all those things. Likewise, whenever we have a composite quantum state, right now we should be in a position to identify that which in that particular composite state, what is the position of which qubit. So their respective positions we should be able to tell. Then only we will be able to like directly apply the quantum gates on specific qubits instead of the entire state. That also is doable, right? And what are the primary quantum gates we have seen? Like we have seen Hadamard gate for superposition. We have seen control NOT gate for control and target, which is a control flip kind of thing. We have seen C phase or controlled phase, which is nothing but a controlled phase. And we have seen only also the basic phase gate, which is Pauli Z matrix, where we have seen that it's a 180-degree shift, and it happens only when my control is 1. So if my control was 0 and my target or my now my current state is 0, nothing will happen. If my control is 0 and my current state is 1, then also nothing will happen. If my control is 1 and my current state is 0, then also nothing will happen. Only when my control is 1 and my target is 1, then my target will be phase rotated by a phase factor of 180-degree. That we have seen. And how it is coming? Like e to the power of I theta, where theta is equals to pi, and e to the power I pi is nothing but -1. So till that part we have seen a basic quantum computing language as well. Okay, where if there is an arbitrary quantum circuit given to us. So right now we know both the things, how to write the quantum computing language. That is a very platform independent one, but with respect to the respective kind of platform that you are using, there might some of the comments will be different, but they should be very well interpretable if you know the basic thing. And if you are asking for no audio, please try to rejoin. Otherwise, others also, I guess, would be having the same problem. Okay. So we have seen this thing, that how to write the quantum programming language. Also, we have seen that how to interpret a quantum circuit with respect to quantum states. Okay, if you are mentioning no audio, is that so? Okay. First slide only. Yes, I have not navigated yet, but audio should be fine. Thank you, Vishaka. Okay. So now I am just starting with the first slide. So before starting, fundamental a few of the classical things we will be discussing. So what is an algorithm? Basically, so algorithm is something that has a certain kind of an input and that has a certain kind of output. Now, theoretically, it is like assume that in order to make it a valid algorithm, or when we can call it an algorithm, is it should at least produce one output. That can be more than one as well, but input should be greater equals to 0, number of inputs. But even with that, the output should is greater equals to 1. So at least one output my algorithm has to generate. Then only it will be called an algorithm. Okay. So consider a problem where each instance has a solution, right? So example of a problem can be is an integer p a prime number. The instance is a particular choice of integer and the solution will be either a yes or a no. If this happens, we call it a decision problem. We know it's a kind of a verification that we are doing. Okay. For example, say, is my graph 3 colorable? That means I am just putting the number of colors as 3 and I will try to plot it based on the rules of graph coloring, that no two adjacent vertices can be colored with the same color. After all those things, if I can do that, doesn't matter whether I need a less number of colors or not, but just if it says a yes, it's a colorable, then we call it decision problem, or we answer a yes or a no. So algorithm is nothing but a detailed step-by-step method for solving any particular problem. The very fundamental things. A computer Turing machine, already these are the things that are discussed, but these are kind of a intersection between computing and all those things and algorithms. So that's why these things are written. Computational complexity, just a very quick recap on what we have seen. Computational complexity comes with respect to the input size that you are actually doing for. And for example, there can be basically, yes, as you can see, there are basically 4 complexity classes that we have, a P, NP, and NP complete and NP hard. Now, P and NP, I think I had discussed. Let me again discuss, but we will focus more on the NP hard and NP complete in terms of what they actually mean, not the theoretical definition only. So what is P? P is nothing but, I told you, if you remember, it's not polynomial. Let us call it perfectly, it's a deterministic polynomial. What do I mean by that? It means if I have a deterministic machine or a deterministic hardware or a computer, then that algorithm, if it takes a polynomial amount of time, then we call it a deterministic polynomial. In short, it is called P, right? So polynomial means basically where n square, n, log n, all these things, where it's a function of n, kind of that, where n is definitely in the base, it is not in the exponent kind of thing, right? Example is any problem, any basic problem that has that kind of a complexity is NP. What is NP? NP are those problems which are doable in polynomial time if we have had a non-deterministic machine. Non-deterministic machine means a very powerful kind of a computing device. Powerful in terms of where I am able to cater my multiple needs simultaneously. The same non-deterministic logic is carried or kind of a propagated here as well, or carried forward. It is the same thing. So if I have a non-deterministic machine where on having a particular input, I can go to multiple steps simultaneously, then that is known as a non-deterministic machine or a non-deterministic logic. In automata theory, you have seen this kind of deterministic and non-deterministic automaton and all those things. But the thing is that what we have with us, the classical systems, all of them are very much of a deterministic logic. So it follows a deterministic logic. Now, if that means that all those instances I have to do sequentially, one after another, not simultaneously. Now, whenever all the possibilities have to explore, definitely, and all of those exploration have to take place sequentially. Now, you can imagine there is a chances of an exponential or a non-polynomial thing coming into account. So that is the thing. So NP is non-polynomial in terms of it is non-polynomial with respect to a deterministic machine, or vice versa, we can say that it is polynomial with respect to a non-deterministic machine. But since we have deterministic machine, we call it NP or non-polynomial. But it should be, theoretically, ideally, you should call it a non-deterministic polynomial, not a non-polynomial. polynomial. Okay, now P and NP is done. Now, what is NP hard? Because NP hard is something, or NP complete is basically a combination or intersection of NP and NP hard. So for that, for a logical flow of understanding, we should first know what is an NP hard problem. So I used to give this example. It's very much relatable, I guess. Say, for example, you have a class. You have a class of students, right? Say for a CSE student, BTech CSE batch of 60 students. Now, say one student or the topper of the CSE batch is anyone who has got a 85% marks or a 95% marks, for example. So he or she is the topper of BTech CSE batch, say 6th semester, for example. Now, a student from IT or the EC electronics is coming to the CSE class and just claiming that, hello, everyone, hello. If you think that you are better than me, no, I am better than any one of you. I may not be like say very superior than you, but at least I am as better or as good as any one of you. At least. That what does it mean? That means there is no student in BTech CSE who is better than that IT student. If that happens, if that happens, we call that IT student or EC student as an NP hard problem. Now, the CSE, BTech CSE is equivalent to NP. It means if a problem, when we can call a problem to be NP hard, when the problem may not be necessarily into NP, but it is claiming that I am as hard as any of the problems that reside in NP class. So I am at least as hard as any of the problems that are already there in NP. If I can claim that as a problem, then I am a problem which is an NP hard problem. So I am as hard as any of the NP problems. That is called NP hard problem. Now, when I can say that I am an NP complete problem, that means the topper of CSE, if he or she stands up and says that, okay, hello, remaining 59 students, just listen. I am as hard as, or I am as good as any one of you. There is no student in these BTech CSE out of all the 59 participants or 59 students who is better than me. So I am at least as good as any of you. If that is the claim, then that BTech CSE student will be called an NP complete problem. So with respect to this scenario, the complexity classes scenario, it means that if a problem itself is in NP, and if that problem is at least as hard as any of the problems that belong within NP, then we call that problem to be a NP complete problem. So it is definitely NP hard because it is at least as hard as any of the problems that are in NP, and also it is in NP. So NP complete is nothing but a kind of a intersection between NP and NP hard. I hope this is clear to everyone. I hope that is clear to everyone. So mathematically, if this is to be written, we call it for all symbol. Just give me a minute. Let me write it down as well. So just a minute. I'm just connecting with the pen tab. So how we can actually write it down is yes. So okay, yes. So we write it down in this way. Let me write over here. So NP hard is basically for all problems L such that, or say L dash, let me call it, say L dash does not belong to NP, but L dash, sorry, for all L it should be, L dash is another problem which does not belong to NP, and L dash is reducible to L, where L itself is in all, represents all problems in NP. Okay, and this less than equal to, this is not less than equal to, it is called a polynomial reduction. This is called a polynomial reduction. So this is the definition, but instead of the definition, this is the basic meaning is this thing. Just remember the story of the computer science and IT or EC class, whatever I mentioned. And for NP complete problem, now you can write it down. So definitely uh, L dash also should belong to NP, and for all L such that if L dash is polynomial time reducible to L, in that particular, and of course L is also all for all L, they belong to NP. If that is the case, then we call L dash to be a, so this is basically L dash is NP hard. This is the mathematical definition, and here it is L dash is NP complete. Okay, I hope it is clear now to everyone. Right. Now again, because slowly we are just transitioning to quantum algorithm and its types. So we have very strategically chosen a certain problems where we can showcase the quantum advantage or quantum supremacy. So this is the example that I also had told you. Now, whenever I made like coin the term hard, you just assume what do I actually mean by a hard problem. Okay, so hardness of a problem is defined by whatever I just explained now with respect to the complexity classes. Uh, so if I have to factor a 300-digit number, so the best algorithm will take these steps, and on a computer at terahertz speed, it will take like this many number of years only for a 300-digit number, which is definitely not possible to be seen by a single person in his lifetime. So this is the something like factorization or integer factorization, where we choose a very large prime number and try to put that what are its constituents. So this idea is used by RSA, and it is also used for a difficulty of because a difficulty of factoring a problem is the basis of the security for RSA encryption scheme. RSA, ECC, DSA, all those schemes. I do not know, is there any mathematical equation to calculate that much of or not? I don't think so. I guess it's a like not that much of an easy one. There are a lot of other factors and coefficients that are into consideration. So these are very like theoretical, I guess, with respect to a lot of approximation. So information security of interest to provide and public interest to, okay, what it is, I know. Information security of interest to private and public sectors. Forget about it. I hope you have understood that factoring is a hard problem. This is the main essence of this thing. Okay, this is how just a big number. So this is basically N, and this is P, and this is Q. And this is a public key encryption algorithm, RSA. Public key encryption means it is also called an asymmetric key encryption. Basic fundamental logic, it's an asymmetric key encryption, means it has every node or every participant present in the encryption scheme or security scheme will be having a pair of keys, one public key and one private. Okay, that is why it's called an asymmetric. So we share a certain amount of like our public key as a receiver. If I want to get some information from your end, say for example, A wants to send something to B. So A has a public key, say for example, sorry, A has a public key, say pub A, and a private A. Similarly, B also has a public B. It's a key, nothing but these are all keys. And it's a private of key of B. So how this communication will take place is, first, in what way encryption will be done. So A will be definitely wants to send, so is the sender and B is the receiver. So while encrypting the plain text, in order to generate the cipher text, what A will be doing, A will be using B's public key, because public key is public definitely. So A will be using the encryption while using the like applying the encryption. A will be using public key of B. And when that cipher text will reach to B, we will actually decrypt it with respect to the private key of B. So while it is having a full duplex communication, then definitely we will be using the public key of A to encrypt the text, and A will be using its own private key to decrypt the text. Likewise, this is a basic concept of RSA or any asymmetric key algorithm. The encryption decryption works in this way. Okay, and this P and Q we can thought of as a public and a private key kind of. Okay. So if I have one, I can tell what is my Q just by dividing n by p. But if n only is given to you, which is a, say, for example, a 300-digit number, so that much of something is given to you, is it really feasible for you to tell that exactly which are the two like factors of that big number that you have taken? And one of them can be public key and one of them can be private key. It's basically not doable because of there are so many number of combinations that you have to check that it's not practically feasible in real time. So quantum algorithms, concept of a quantum computer emerged as a universal device to execute such quantum algorithms. There may be quantum systems that cannot be simulated efficiently on a classical computer. We have seen what are the cases in our day one class. Okay. There are a certain cases. What are those cases existing in classical, which generally is very difficult to be solved using the classical ones because of the time, space, the simulation inability, and all those stuffs. And we cannot enter quantumly. These were the four aspects. So both of them like propose that machines using quantum processes might be able to perform computations that classical computers can only perform very poorly. Today, if possible, if time permits, we will actually see a certain kind of at least the advantage of a quantum algorithm with respect to a classical algorithm in a very detailed way. We'll actually see in front of our eyes that, oh, yes, you can actually visualize a quantum advantage. Maybe that is not very significant advantage, but it is definitely a certain kind of an advantage with respect to the best possible algorithm for that problem in our classical setup. Okay. So factoring with quantum system, this is the same thing. I'm not skipping this thing. Implications also, I've told you. Okay. So, and also know one thing, for a non-deterministic machine, just like your deterministic machine works on a certain kind of an algorithm, which are based on a deterministic algorithm, you can say. A non-deterministic machine or a quantum machine need certain kind of a different algorithm. It cannot be your very well-known classical algorithm. In easy words, say I know greedy technique, right? So directly the greedy technique as I know it, or say divide and conquer. Mart sort. We all know the algorithm of Mart sort. We all know the algorithm of quick sort. Can I directly encode the quick sort algorithm into a quantum computer? Answer is a big no. Why? Because that is not the way a quantum computer can work. Computer is ready, hardware is ready, then also you need an algorithm in order to make the quantum computer know that in what way it can process its quantum states. So for that, and what do you mean by ultimately a quantum algorithm is basically a set of or a list of quantum operations. What is a quantum operation? A list of quantum gates. And how your quantum algorithm will look like ultimately, if you are able to implement it, your quantum algorithm will look like a quantum circuit, which exactly we have seen in our last class. Now that is an arbitrary order we have taken. But if you are able to design that order, that whether on first qubit I should be applying Hadamard, then on second qubit it should be a controlled phase gate, then on third let me again apply a Hadamard, then from third to first it will be a control to target not gate. Likewise, if you are able to devise this logic, then that is called a quantum algorithm. Okay. Okay, till this part, is it okay to everyone? Is it okay till this part? Okay. Okay. Thank you. Thank you. Okay. So now we have the base. We have understood that, okay, classical algorithms are not going to work here. We need a certain different kind of an algorithm. Let us see now how difficult it is or whether it is easy or how we can frame a quantum algorithm with respect to the quantum gates and circuit. So what makes a quantum algorithm potentially faster than a classical one? We all have seen a few things. It first is a quantum parallelism. So since quantum provides superposition facility or a quantum mechanical principle is superposition, so we have to now utilize that kind of a parallelism or speed up in our quantum algorithm. But if we are able to do that, at least it will offer us parallelism. So that is a quantum parallelism. By using superpositions of quantum states. The computer is executing the algorithm on all possible inputs at once. Okay, we can do that. Multiple state computing will be happening at the same time. Second one is the dimension of quantum Hilbert space. Now, Hilbert space, if you know, it's a like extension of an inner product space where we think it of like an infinite space or like complete state of all states that is possible. We should be able to plot or map or encode every possible state that can take place. So 0, 1, yes. 0, 0, 0, 1, 1, 0, 1, 1, yes. 0, 0, 0, 0, 0, 1, 0, 1, 0 till 1, 1, 1, yes. 0, 0, 0, 0 up to say 100 times plus 0, 0, 0, all those zeros followed by last one, and that many combination of like states that you can encode theoretically. It's a yes because of the dimensionality of the Hilbert space. So the space itself is not a problem in for quantum, so because it is exponentially larger. But all these things are theoretical. Again, I'm telling these are theoretical. These are some factor of a certain practical limitations as well, depending on the decoherence, depending on the error, and all those things. Okay, and we also should be able to differentiate between two quantum states. So though Hilbert space exists, it is theoretical. How quantum algorithms differ from classical algorithm, we will just see it in the way we will encode it. But definitely, at least we can understand something that classical algorithms do not give us any exponential space to work on. It do not provide us any kind of a parallelism, and definitely it does not have any entanglement capability. And for quantum, it is different subsystems in a quantum computer may become entangled. Always put a focus on may, even for superposition. So may become entangled, exhibiting non-classical correlations. Okay. And we do not really know what makes quantum systems more powerful than a classical computer. We actually know it, but okay, maybe in some other form. And quantum algorithms are helping us understand the computational power of quantum versus classical systems. Definitely. We will be in real time be able to non-symmetric quantum channel of states. Oh, there are so many technical things. Just put it in easy words. Non-symmetric something quantum state. Well, otherwise, just at the end of our class, let us discuss. So quantum algorithms are helping us understand the computational power of quantum versus classical systems in terms of how many queries or what is the time taken in order to solve any particular problem. This is the basic workflow. So for example, we have a traveling salesman problem or any problem we can have. So initially for a quantum algorithm, it should be having a problem definition followed by a quantum. Once we have a problem definition, we have understood the resources and all, then we will be framing the quantum algorithm. Once we frame the algorithm, we will try to plot it with respect to the physical libraries that we have. That is, we have to devise the kind of quantum gates corresponding to the quantum algorithm so that the resultant is the same for the algorithm as well as the circuit implementation. Once I have devised the circuit, then I will put it to the quantum compiler. So for compilation and all. And once it is done, it can actually be put to two different systems. First one is the quantum processor and the second one is a quantum simulator. Okay. So quantum processor means it is a real quantum computer, and a quantum simulator means it is ultimately a classical system, but it is able to simulate the behavior of the quantum ones. Why we use it today? Because a simulator say with a more number of qubits, which we are just simulating, that is possible. So for experimental purposes, we can use it, but definitely we will not get the exact result. It will be very much of a biased thing, or maybe perfectly unbiased, but that will not encode the current state of the error of the quantum system or what it is exactly offering. Some deviated output we will be seeing. We just mimic the way it works. We encode everything. We encode everything manually. Say, for example, all those combinations actually we have put it in a simulator. So ultimately, it's a classical one only. But it is just some high speed something that is able to show that, tell me that, okay, if So ideally, it's just like a mathematical model. कि अगर ऐसे ऐसे आप देते हो तो it will perform it, and if you are able to simulate it or perform it say simultaneously, then this much of time should be taken. All those things. That is a kind of a simulator that they have, but it's not a real quantum processor. What do I mean? Say for example, if I give you one Hadamard gate, then my and put a zero. After Hadamard, what can happen? It's a K0 plus K1 by root over of 2. Right? In simple words, it's 50% probability of 0 and 50% probability of 1. How 50% is coming? 1 by root 2 is the probabilistic amplitude of K0 and K1 both. So probabilities will be 1 by root 2 whole square, that is half, into 100%, so 50%. Exactly this thing will happen if you put it in a simulator. But if you put it in a processor, you might get certain different output. Maybe it's a 51.23% get 0, 49 point whatever percent, 6-7% or something get 1. Or it can be some other result. So it has no quantum element in it. It just simulates it. Some of you have worked on the simulation, I guess. So it just like that. It simulates that if it is able to execute this parallelly, then this should be the output, or this should be the ideal case, what it should be able to give you. But again, I'm telling these are all the ideal cases. The actual ones are different. How much quantum gate performs in a single qubit is invalid question. Why I'm telling you? Because first of all, a quantum gate, whenever it is working on qubit, whatever it is, depending on your at some instance where you are standing, so on that respective state, you can perform the operation. That is not an issue. That is not an issue. So with respect to a certain states, now you can ask me that are you can you say that the operation will not affect because it has maybe taken place so many times on that thing? In reversible logic, it should not. Or you have to think of putting or regenerating the state again somewhere in between, so that that kind of a whatever deviation you might be thinking right now, that will not affect. So it is based on again your requirement. No, you do not need to purchase any simulator. Simulator you can get from normal simulator. IBM also provides it. So it's very easy one, and with more number of qubits also, I guess they are providing. Right now, I do not know how many qubit simulator they are providing. But at least for your basic because otherwise, if a real quantum computer if you want to purchase, I think with respect to certain usage of it, you have to pay literally quite a good amount of money. So for experimentation, real computer, when I done it in the last time, it was I guess 7 qubit something. So उसका भी availability का कुछ issue होता है. So there is a queue. So there is a queuing delay and all those things. So real calculation is bit difficult if you do not purchase it. But if you have a dedicated like quantum processor, then you can definitely do the calculations. Otherwise, only for initial stages, you can think of whatever what you want to like perform, you can think it of to do it on a quantum simulator. But definitely with the free available real quantum processor also, you can try to compare the experimental results and see how much is the deviation from the simulator one as well as with respect to the real ones. That you can. Whether to buy or not, but why you should be buying a simulator? If you want to buy, then buy a real quantum processor, or at least certain. You cannot buy the full quantum computer, but at least some of the based on again a very like your required usage. You can buy like 1% of the entire thing for 1 year or 1 month. I don't know what is the scheme for that. You need to connect with the sales team for that. What is the current rate and all that you can think of, but you do not need to really like hire or say buy some simulator. They are available on me. Okay. Second is now we will enter into now till now what we have seen the complexity classes. We have seen that okay, classical algorithms are not going to work over here. So we need a certain kind of a different algorithm, which is called a quantum algorithm, and also what can be a quantum algorithm workflow. Okay. And some of the like features like parallelism, entanglement, all those things, and infinite encoding theoretically at least infinite encoding possible into our quantum steps for a quantum algorithm, which is not possible in a classical algorithm. So all these features we have seen. Right now, we will enter into, right now, what is the time? Let me keep all these things. So right now, what is the time now? 2:41. Okay. Let me enter into the types of quantum algorithms. So these are also called algorithm operators or say quantum operators or type of quantum algorithm, whatever you call it. All of them are same thing. So these are very basic 5 category or classification or categories of this. First one is a quantum Fourier transformation. Okay. Kind of a classical analog to the classical discrete Fourier transform or something. But this is how it can work. And second one is based on a second one. Don't ask a direct question. We will come to that QFT thing later. Algorithms based on QAA, which is a quantum amplitude amplification. Okay. Third one is based on the quantum simulation ones. Fourth one is a adiabatic method of algorithms or adiabatic algorithms. And fifth one is algorithms based on quantum walk, which is analogous to classical random walk. So quantum Fourier transform, again, it is a very big concept itself. So maybe if we get a chance tomorrow, I will choose any one of the algorithms, maybe Grover or Shor, depending on the time provided, because both are very bulky algorithms. Try to cover a fundamental level both the algorithms tomorrow. But in a nutshell, you can think it of in this way that quantum Fourier transform does not work on the computational basis. Firstly, what is a computational basis? Computational basis means whatever you have 0, 1, ket 0, ket 1, ket 0, 0, ket 0, 1, ket 1, 0, ket 1, 1. So whatever we have with respect to the z axis, if you refer it, it is also known as the measurement axis and all. So that is basically your computational basis. But QFT requires the quantum states to be into Fourier basis. Okay. So it's basically with respect to Fourier transform is nothing but it decomposes a function of time into frequencies. So ultimately, see, with respect to time, I am just right now moving to the frequencies thing. Now, simply or try to like visualize in this way. Say, for example, initially you have a cake. Just think of an example of a cake or pizza. For example, simple one. Okay, just a circle. Say it's a pizza. Now, what we can do first, it is a single piece pizza only. No divisions are done on it. Let me assume it. So first we are breaking it into 2. Then we can call it a 0th one and the first one. So then I can encode 0 and 1 with it. Yes. Now say I'm dividing it another into a vertical bar was there, another horizontally. So right now 4 quadrants will be there 0, 0, 0, 1, 1, 0 and 1, 1. Now if I again break it, again put another say frequency division, then it will become 8. Likewise, it will be having with respect to everything. So once that entire thing, say 0, 0, 0, 1, 1, 0 and 1, 1 I have, if I put for every such sub or say quadrant, if I make another say vertical line or say some small partition, then it will be 0, 0. Then left side of the quadrant is 0 and the right hand side of the quadrant is 1. Think of any clock or think of any pizza, think of any such thing, say cake, whatever you call it. So likewise, in this way, right now we want to encode multiple things here, which is for the frequencies one. And this is a very big discussion. We will do it, but not right now. It is not our agenda. Okay. But basically, it's like a simple decomposition, the discrete Fourier transform on amplitudes that can be implemented as a quantum circuit consisting of Hadamard gate and controlled rotation or controlled phase shift gate. So just see the quantum circuit, or at least tell me what are the quantum gates available. You can see there is Hadamard gate with respect to H. You can see at the like these two are swap gates, right? And this U rot, okay, this is a unitary rotation gate. which is nothing but the control phase. It can be multi-controlled, definitely, depending on how many control you are using. It can be multi-controlled, it can be single control. That depends on your individual implementation. Okay. And why this kind of thing is very important? Because Shor's algorithm relies on QFT. So as of now, just remember that Shor's algorithm uses QFT for its integer factorization. Okay. And through QFT, it has shown that the RSA algorithm, or the integer factoring method, which was earlier exponential time taking, right now he reduced it to polynomial. So Shor showed an exponential speed up of integer factorization. Okay, or discrete logarithm. Both the problems are same thing, just like complement of each other, you can say, through this QFT thing. And he has showed the exponential speed up, or kind of quantum supremacy. Another one is quantum amplitude amplification. Basically, Grover works on this technique. So Shor's algorithm is based on QFT, and Grover's algorithm is based on quantum amplitude amplification. Where again, do not look into the images, you will not be understanding anything. Just remember one thing, the basic method is amplitude amplification is very simple. That first, say for example, I have to find a needle in a haystack or haystack kind of thing, where I have unsorted any place, I want to find something. Okay, if you have seen the robot movie, so kind of they used to have a certain mechanism where all the heads will be rotated. So the one who is not rotated can be easily identified. So here also in Grover, the same kind of logic is followed, so that they want to identify that particular one who is the culprit. Where you want to, maybe your ultimate, the result should be there. First, you have to identify it. So that kind of a identification is done through a phase shift first. Okay. So it's kind of this thing. So for example, initially I have a superposed state of all these things, right? So first technique in amplitude amplification is, Grover is, I will be first identifying the one, maybe this is the one. So 1, 2, 3, 4, I will just invert it with respect to 180 degree, or change its phase and make it like this. Okay. Now, once I have this, I will be doing certain steps. Basically, from here, I will be calculating the mean now, or average of all the probabilities or probability amplitudes, or some of the values of it, coefficients. Then I will be applying an inversion about or with respect to the mean. Now, once I do that, it will, at one step, just immediately after this, if I apply it, it will be like all the other amplitudes or all the other vectors, which is not my target vector, their amplitudes will be diminished, a little diminished. And this one, it will go up and it will just become this. So this is the first one. Again, I will be doing the same thing. Again, I will be calculating the inversion and all those things. Right? So subsequently, after all these steps, it will be like very small values, which is almost negligible, and one big value. There are steps, which is called an inversion about the mean operator. It is used in Grover. It's kind of a similar logic in amplitude amplification, but Grover is little advanced of QAA. Kind of that. So it is amplifying a particular amplitude where I want to find a solution, or maybe where my solution resides. This is an amplitude amplification. And primarily, Grover has shown that if I perform root over of n times these iterations, after my phase shift is done, okay, I have identified and changed its phase. If I perform this kind of an iteration, inversion about the mean, like just diminishing the amplitude of others and increasing the amplitude of the desired one. If I keep on doing it root over of n times, then I will be exactly able to find the data item from that unsorted database in polynomial type. I will be able to do that. So initially it was order of n iterations in our classical setup, when we used to had a kind of a linear search that we can apply. Considering we have space complexity, or space is not infinite, or there is no hashing, there is no other thing, or any other sort of data structure that we are using. If we just have a database of unstructured, unsorted data, Then in linear search, in worst case, it will be taking n minus 1 number of queries, or which is big of n iterations. Okay. But in Grover, in quantum, it is big of root over of n number of iterations. So n has become root n. So this is a quadratic speedup. Okay. Hadamard transform are applied on all the qubits. But this is a technique. Okay. Forget about it. Third one, so QFT and QA is gone. Basically, two of the like bulk algorithms like Shor's and Grover, they have taken it. Now, the third one is quantum simulation algorithms. So where you think of simulating a given Hamiltonian by breaking it into a sum of the simpler ones. So this is your simulation technique, where you have to go in the quantum level. This is not a classical simulation in a quantum hardware. It is not a quantum simulator. Do not mix up the two things. The first one, as we have seen in the algorithm workflow, the quantum processor and the quantum simulator, that is just a classical simulator. Quantum simulation means simulation itself is happening at the quantum level. So there is a quantum particle that we are using for simulation. These two are different things. So quantum simulator would efficiently generate qubit string states that closely approximates the physical states obtained from a broad class of dynamic evolutions. Implementation is to calculate say molecular energy or ground state energy on an NMR for simulating a hydrogen molecule. So these are itself, you can understand that these are something which is happening at the nanoscopic level. Okay, that is quantum simulation. It is so big and yet so unexplored. This one is a quantum adiabatic algorithm. So this is what D-Wave uses. Though D-Wave uses a superconducting qubit, just like IBM, Rigetti, all of them, but its technique itself is based on the adiabatic algorithm logic, which is like this. Say, for example, if you remember, maybe in day 1 or day 2, I was telling about the simulated annealing and quantum tunneling things. So these are a few things that I was discussing, or I had discussed, I guess. Simulated annealing. Let me just write it down. Simulated annealing. Then it was quantum annealing, or it is also, or say quantum tunneling. Okay, so simulated annealing is, think it of as a say big kind of ground where there are a certain kind of say क्या बोलते हैं इसको, say it's just like this. Say for example, there are certain kind of this thing. So if I am somewhere in between this or here, somewhere here, so I will be unable to tell. I will be unable to tell that whether it's the minimal, whether it's a minimum point, or there is some other point in this ground which is minimum. So I cannot tell that, right? So every time I will be stuck in somewhere thinking that it is my ideal solution, but maybe there is a better solution that exists in that, say, playground, or in that space, technically. So that is a problem that we used to have in simulated annealing. It starts from local optima. Global minima or global optima can never be obtained in case of a simulated annealing. Then quantum came into picture that, okay, so why this thing happens? Why this thing happens? This thing happens because if I'm here, I cannot see what is happening here. That was the challenge. If I am in this position, I will be unable to tell that what is happening on the other side of the say wave, or other side of the car, or the other side of the mountain, or whatever you call it, physically, logically, whatever it is, but I cannot be present there. Now quantum says, okay, but I have that possibility. I can be present at both the places simultaneously. How? True, because I have a wave nature of mind. So I can behave, or I can say reside in form of a quantum wave with a certain probability. I will be here, say with a probability alpha, and here also with a probability beta. So as if now you can think it of as if in this particular thing, there is a tunnel kind of thing. So I can actually to make a to and fro. I can go and I can come back, and I can actually, that means that I have a possibility to be or to tunnel through that particular barrier. This concept is called quantum tunneling. And once we had this, see the tunnel effect, see the image, the tunnel effect. Since we have a tunnel effect, so if we are stuck here, we will not reside over here, because whenever we are here, we will also be here in this position, right? So one and one, we both can be, like in both positions we can be with a certain probability, but at least there is a probability that I can see this part. Now once I am here, again I will see that this is the minimum. Now once I am here also, I can see this thing, right? So I will be tunneling through this curve and I will be here. So 2 and 2, they are same. Now once I am here, I will see that if I do not find anything, then I will call, okay, this is my global minima. So this is a tunnel effect, simple. Just like we have our tunnel where we can actually, in a mountain, we have seen the tunnel thing. We can actually be in both the positions if we travel through the tunnel. Similarly, quantum particles also are thought of to be traveling through the tunnel because of the wave nature of the quantum particle. So maybe this position, if I call this position, say with respect to say P1, and this position is say P2, and particularly this thing can be described as a quantum wave, say P1 state, whatever state I have of P1, with a probability say alpha, the coefficient alpha plus beta, and that probability. So this kind of superposition holds, right? So I can be in P1 with alpha square probability, and I can be in P2 position with beta square probability. Now let that beta be as minimum as possible, but still it exists. Okay, still it exists. Okay, great. Now adiabatic evolution is absolutely related to this idea, where we see that, okay, just see the image, don't just stuck. Yes, absolutely, we can use it. Gradient descent, very much you can use the same idea. So adiabatic evolution means that adiabatic means very slow, very slowly if you just do it. So the result will be, at the end you will ultimately like result in the lowest state itself through the adiabatic process. Adiabatic means just very slowly, if you just uh, do the evolution of the quantum states with all the probabilities and all, then the one state where it is the solution state, it will be encoded into your ground state, and through the gradual evolution, all the higher energy states will actually get vanished with courses of time, because that is not a stable state. But the ground state, where you have encoded your actual solution through your Hamiltonian, if you encode it, you will see that that is the ultimate result that you are getting. And this is a physical phenomena, mostly a physical phenomena, not a really computing one. And this idea is used by D-Wave. Okay. So I'm just writing 2 points also here. Just remember, we have two models of computation. We have two models of computation. Sorry. First model is called the gate model of computation, or it is also called the circuit model of computation. Okay. And also another one is, we have this annealing model or adiabatic model of computation. So annealing model and adiabatic gate model are completely different. And all the companies like IBM, Rigetti, say Google, all of them uses this gate model. That is why it is more thought of a universal model of computation. It is also called universal model of computation. And the annealing model is used by D-Wave, this company. They have reached to another level with respect to the annealing model development and all those things, but still it is not very reliable. Though we call that we have a 5,000 qubit of a quantum computer available by D-Wave, which is an annealing model of annealing quantum computer, but it is not very reliable in terms of encoding the problems. Though for gate model we have very minimum number of qubits, But since it is kind of a versatile, so you want to rely on that. Instead of only increasing the number of qubits, our approach should be, or our objective should also be, to make it applicable as many cases as possible. Just think it of the Xerox machine. Xerox machine we can maybe develop that can clone one quantum state, but that is not a universal Xerox machine. If I have just a machine that can like say print or say clone exactly one page of mine with a certain kind of an information on it, can I call it a Xerox machine if I give an another page and it is unable to clone it? So we will not call that. So that is why do not compare with respect to qubits that, okay, so DWF 1 is very superior or more superior than the gate 1, because I have here 5,000 qubit that D-Wave is providing. I-Wave is right now providing, say, 60 qubit or say 20 qubit quantum computer. So it is very less powerful than D-Wave. Nothing like that. The entire approach is different. Their architecture is different. Here in annealing model or D-Wave, they use as a kind of a different data structure called chimera graph. Itself is different. There is a lot of error terms associated with it, but because of its like scalable architecture, they are able to incorporate more number of qubits. But again, I'm telling you, the more number of qubit does not necessarily imply a better outcome or any sort of superiority of quantum hardware. I hope that is clear. Generally we do not do that. We do not really, we use different problems. Yes, why I'm telling this, because in like even a lot of companies are there which I do not know why they rely on D-Wave, because and they had this logic only that D-Wave ka number of qubits is more, so that is more like flexible. We can do a lot of things with the D-Wave thing. Nothing like that. It is absolutely wrong. But definitely there is a point that is a fixed type of problems जिसका नेचर ऐसा है जो काम कर सकता है इन द एनिलिंग मॉडल, एंड वी कॉल दैट वन अ क्यूबो or a quantum unconstrained binary optimization problem. So for certain kind of a constraint optimization problems and unconstrained optimization problems, again for very easy ones, again I'm telling, so those problems you can um, again, yes, absolutely. So there is a specific type of problem that works better with the D-Wave one, because those many parameters right now, you cannot really rely on for the GET model. But again, GET model, once it is built, it is able to perform your set of computation for the optimization once as well. But right now, maybe you cannot do a lot of things with that. So that is why right now in this NISQ era, noisy intermediate scale quantum era, if you want to have some for optimization, if you want to use some quantum computer or hardware, you can rely on annealing model. That is the thing. But for quantum communication, cryptography, for other any of the computing tasks, it's better to go for the circuit model or the gate model. Okay. Then it's random walk. So random walk is a simulation of a random movement of a particle around the graph. And see there, the way they actually work, adiabatic is different completely. Simulation is completely different. Amplitude amplification completely different. Fourier transform completely different. So they are like totally different. It is not like that one is an advancement of the another one, or there is any chronological order that you should be learning in this way. Nothing like that. So they are completely different in the way they work. So random walk is basically a simulation of random movement of a particle around the world. So there is a time dependency of random walk. It can be either a discrete time random walk or a continuous time random walk. Okay. Now exists a quantum analog of classical random walk. Do not call quantum random walk because quantum itself is random. So this is basically like two redundant words. So just use either quantum walk or classical random walk. Okay. So quantum walk is a quantum analog of classical random walk. The physical intuition behind a classical random walk, if you're in position 1, is basically say at every point 1, 2, 3, 4, 5, 6, what is the probability that the traveler or the particle can move? So 0 will be with 100% probability it will go to 1. Now from 1 with a half probability it can go to 2 and 3. This is the way the classical random walk works. That is the illustration. Now from 2 and 3 again, it's like I am converging to 4, so it will be 1. And again from 4, I am going to 5 and 6 at time instance 3, so it's half and half. Likewise, you can see. But discrete time quantum works is a different thing. It is not exactly the way classical random walk operators you can design. So discrete time quantum work with two basic operators. First one is the coin operator and second one is the shift operator. Okay. A coin operator is nothing but the Hadamard gate. What it is, how it works, I will explain just after that. As of now, just remember or understand it this way. Say this is a drunkard. Okay. Some drunkard. Now how a drunkard works or he may work like either left and right, then again from that point again some left and right. That is very randomly he will be walking, right? That is how a drunkard generally works. Okay, so similar logic you can think it of with respect to the discrete time quantum walk as well, where uh, where like coin operator is it can either go to, it can basically go to both left and right. Okay, now depending on that thing or depending on say coin outcome, it will make a shift, conditional shift. So basically it works in this way. Say the operator, mathematically they are described in this way. Say for example, Walker is replaced by a quantum particle carrying a two-state quantum system for a coin, and coin toss is affected by an unitary operator. Basis state of quantum walk is an ordered pair of X and C, where X, the first position, is the position itself of the drunkard, and C is the state of the coin that he is tossing basically. So coin operator is a Hadamard one. So see here, this HX0, this thing is X is the position. I'm not doing anything with X. But if I got a 0 through the coin toss, what I will be doing is, I will be, whenever I'm doing a 0, I will be making it 0 plus 1. State of the coin. If I have a 0, I will make it a K0 plus K1 by root 2. I'm just keeping the 1 by root 2 outside. So it will be x comma 0 plus x comma 1. What is x comma 0 and difference between x comma 0 and 0? Basically nothing till this point. X is just, we are writing it in this way. Instead of only C, we are writing it in this, the form of a x comma C. So H on Ket1, ignore this X as of now. So H on Ket1 will give me Ket0 minus Ket1 by root. Now these two equations are clear. So shift operation now acts on the basis state as, now after Hadamard, I will be applying a conditional shift. What is the condition? Right now, if you are having a value 0 over here as your state, coin state, just go a position left. Okay, so now your X will be X minus 1. So if initially you were on 0, so basically, say for example, you were at a position 0 and you got a 0. So it means you will be going a position minus 1, 0. X is position on the say number line. So definitely it can be minus. Okay. Say for example, if you have say 2 comma 1, you will be going to, since you have 1, so it will be 1 and this will be plus 1. So it will be 3, 1. Get 3, 1. Okay. Now just see it. Now just see it. This is how a three-step of the discrete quantum walk can be defined. 3-step. Okay. So first it is what position? Just don't forget X. First position is the which is the position. Second is the state of the coin. So this is position and this is state. Similarly, this is position and this one is the state. Okay. So you have a Hadamard over here. So SH cube can be written as SH square into S into Hadamard times 0, 0. Okay, I'm just writing few lines so that you understand it. So this will be exactly this. Let me put all the remaining things as it is. So this will be nothing but what will be have values I'll be having 1 by root 2. Then get 0, 0. This 0 is as it is. This 0 is here 0 plus this it will be 0, this 0, first 0 as it is, and this 0 will now become 1. let me keep this thing again same. So shift means no state expansion will take place. Just like in Hadamard, there will be at every step, there will be a state expansion. But for shift, only the phase or the position with respect to 0 or 1 will change. Either it will be -1 or it will be +1. So 1 by root 2 will be this times, since this is 0, so it will become -1, 0, and this is 1, so it will become 1 and 1. Okay, let me just write one more step of Hadamard so that you have a better understanding. Now it's say sh 1 times s times h. So h, I am keeping half 1 by root over here, so h now will be applied on -1, 0, right? -1, 0 plus this thing 1, 1. Just to tell you one thing, this position -1 and 1 unchanged. Now again 0 will be expanded. So 0 will now become first a 0, another 1. And this 1 will become 0. Oh, this one will become 0, and this one will also be -1. Likewise, just let me write. So this is 1, sorry. So just a minute. So where is it? Yes, so this is 1, comma -1. This is 1, comma 0, all plus in between. And this one is -1, comma 1. And this one is -1, comma 0. Just see it over here. I hope right now you can actually make all the expansion. So -1, 0 plus -1, 1 plus 1, 0 -1, 1. Why I am getting over here this thing? Because Hadamard on 0 will give you ket 0 plus ket 1 by root 2, and Hadamard on 1 will give you ket 0 minus ket 1 by. I hope it is clear now that with respect to position, just I'm writing. But because the first bit is for position and the second bit is for the state of the code. So state will be expanded based on 0 or 1. Okay. Okay, these are a few slides that I had kept here, but I'm just keeping them. Just a minute. Let me just remove a few things. Yes, a few slides I was putting there. Okay. Right now it's 3:15. I was planning for a break at 3:15. So yes, just this slide. Okay. Just I'll give a break now for 5 minutes. Then again from 3:20 we will start. Just see the same thing in the diagram form. Okay. From every position, depending on head and tail, I'm just how I'm shifting. So after these things, just see, this is say iteration 1, iteration 2, iteration 3, iteration number 4. So at this stage, you can see that there is a position where you are finding maximum of your, say, footprint kind of thing. So here also in this way, you can amplify the position. Now, this is just a algorithm. Now, your target, for your particular problem solution, you have to encode or use this particular algorithm or this particular algorithmic technique into your solution so that it gives you the correct result. Just like Grover uses the amplitude amplification, Shor uses QFT. Anyway, Shor discovered QFT itself first, then he used that thing for like his algorithm. But these are something that if you are able to encode your particular problem with respect to this technique, then you can uh, develop some algorithm with this. Okay. Yes. So triangle finding is just one example of this one. There are different approaches. I'm not going into it. Okay. Okay. Wait a second. Then I will enter. Okay. So 10 minutes. Then from 3:30 to 4:30, we will see the algorithms. Direct the algorithm we'll see. Okay. Let's take a break now. Let's then come back. Okay. Just a 5 minutes break. It's 3:16, so we will come back at 3:21. Okay. We can start now.
Yes, ma'am. We can start. I think. Yeah.
Yes. Oh, so just like slides are visible, screen visible to all of you. Okay, thank you, thank you. So since we mentioned that we have two different types of like classical random walk, continuous time random walk and discrete time random walk. Similarly, here also in quantum walk, we have two different types of it. First is discrete time quantum walk, which is also called Drunkard's walk. We just have seen that it uses two operators called these kind of shift and Hadamard. Basically, Hadamard followed by a shift, or coin followed by a shift. Another category is a continuous time quantum walk. So here again, from the like term continuous, you can understand that we will be hopping with respect to one position or one vertex to another vertex, but that will happen with a very, like, in so finite level, with a certain kind of a transition probability, that it seems like a continuous one. That is the very essence of continuous time quantum walk. So it seems that it shows a kind of a overall time evolution of a system. Okay. So directly, let me take this example. So how it looks like, or where you can see an application of this thing. So this is a binary welded tree problem. So binary welded tree is something like, you can see there are two binary trees. There are two. This is the first binary tree in this way, in this position. It is this is the root basically. Okay, right now it's had two child, left and right likewise, and this is another binary tree. So this is the second tree, and this is the first tree. And for those who do not, I guess all of you know, if you just want me to give a recap of binary tree, a tree, all of you know that a cyclic connected graph is called a tree. Graph is nothing but a collection of vertices and edges, and if there is no cycle, it's called a tree. And what is the definition of a binary tree? Binary tree means where every node can have maximum two number of children. Okay, so binary does not necessarily mean it has to have two children. It means that number of children should be less than equals to 2. That is, some node might have 0 child, or that is no child, or exactly one child, or two number of children. Number of child. Then it is called a binary tree. Right? A three-array tree is same, less than equal to 3 children. An n-array tree is same, less than equal to n children. Likewise, we follow. So here, from an entrance till an exit, we are thinking right now, say for example, a search engine optimization problem, where different keywords are associated in this way. Where the logical connections is this till first tree, and the logical connection for a second tree with respect to the its keyword match is this one, second tree. Now in between this is a welding. This is called a welding, where it can have any kind of combination. Now, when it was static, it was very okay to do. But the real challenge was when it was a random welding or a dynamic welding. Okay, so here in these kind of cases, we use the concept of a continuous time quantum walk. How that's a very big thing. That itself is another chapter. How this continuous time quantum walk might work on the BWT or binary welded tree problem, but you can think it of this as an application, or this kind of an where from one exactly from one node you can be in both these nodes simultaneously with a certain probability. We will believe that from this node and this node you can reach instantaneously. That is the belief of the continuous time quantum walk. Okay, so that is the transition probability is very instantaneous, and this is a huge application in these kind of problems, BWT. This is just a BW tree while we were solving. This was one of like my work. So I was working on this problem. That is why I can show you a certain kind of a quantum circuit where 1, 2, 3, 7, these are just the pairs or how they were actually entangling with respect to the output. So this is just was the circuit of that quantum thing. Okay. It's very particular problem specific. So and the our algorithm was working in this way. So if we have a like a 4 number of qubits and enter the each color, I'm entering some certain color for the graph 8, enter how many pairs are there, then accordingly your source end, source end, source end, it was showing as an output, welding or pairs of all the adjacent vertices. And since our problem was if it is dynamic, then how we can incorporate it. So we used a certain kind of a multi-control Toffoli MCT gate. As you can see, MCT gate is nothing but a certain kind of a composition of Toffoli and C naught. Okay, and of course there are certain like temporary register or ancillary registers are there, but these are for just to hold the temporary value. And likewise with a certain MCT logic, we actually solve this problem. So our algorithm was able to generate the multi-control Toffoli gate. Yes, definitely. Definitely. The solid ones and that like hollow bubble, definitely they have a meaning. Otherwise, why would it be? And this is a picture of a real quantum circuit only. Okay. And okay, now coming to machine learning, I guess in on 22nd, you will be having certain more of a exposure of QML, quantum machine learning. Quantum Works code available. I have to search. If I find it, if you just ask me, just send me a mail. Then if I get certain any other material also related to that, I will post. Okay. So what I was telling is on 22nd, maybe if I'm not wrong, something related to QML, you are going to get that idea. So, but basically right now it has developed so much, like so much, but there are certain kind of problems where our machine learning works. And again, for machine learning there is an algorithm called HHL algorithm, Harrow Hasidim Lloyd algorithm. This algorithm is the most promising algorithm for quantum machine learning, and it is thought, or it actually theoretically has proven to give another time just after the QFT and Shor an exponential speed up with respect to the classical machine learning. So mostly, very broadly, I will be discussing just 1 or 2 minutes for this. So basically, QML right now is becoming a booming field because of a very few reasons. That is, right now we want something in the next era. We want something as a hybrid model of computation, right? Where we will be having a certain kind of a classical thing and a particular subroutine which is computationally very say intensive. We will put it in the quantum part, and then output we will be getting from quantum. Based on that output, we will be doing a certain kind of modification in terms of our number of inputs, that whatever we are giving to through the classical machine. So this is kind of certain areas where we are right now focusing into for the hybrid computing model. And this hybrid computation has certain kind of a very promising applications, or if you can build up that kind of hybrid system, it can have good application for quantum machine learning as well. Of course, this much is not the theory. We'll be having some better idea from some other professor maybe. So the concept is, yes, let's skip this part. Again, it will take a lot of time. But I hope this is a perceptron model. Those who are working on ML, you have seen these things. Okay. Let me just skip this part because it will be covered. Why I have put it over here so that you have an idea that, okay, this is another algorithm, but it's very specific to QML. So it's better to learn it over there. And it works for the linear systems, like linear system. That is why it's also called quantum linear system algorithm. Okay. So there are a certain subroutine. Again, you can see in HHL, QFT is a subroutine, which I have told you. Simulate quantum simulation, another subroutine. Quantum phase estimation, I will be telling if I get a chance to cover, sure, fully. Then the quantum Fourier transform and quantum phase estimation, both the things I'll be covering. Okay. Quantum phase estimation, where we are actually estimate the phase. Phase means the angle that we actually try to estimate. Quantum phase kickback, it's another technique. Quantum amplitude amplification, I have told you. And uncomputation trick is another one. Okay, so all these things together forms the HHL. Okay, so right now we have done the basics of quantum algorithms, its types and all those things. So it's now time to enter and see a certain kind of real quantum algorithm, how to build up and how they work, what is the quantum circuit corresponding to the algorithm, and what is the interpretation. So we are going to like again enter into a like world of mathematics for the last 1 hour. So for those who just put your like focus, that is what I can say. Yes, so the slides are there. We don't need the slide now. Say, for example, just post the slide. Let me tell you. If I just start explaining from the slide, I will be unable to explain. That is why. Let me just add a few pages. Then start it. If required, we will take more. Okay. So, yes. So now what we want is, we have seen that very few quantum algorithms and all those things, but we have not yet seen any basic implementation of any of the quantum algorithms. So right now what we want to start with is very basic quantum algorithms. Basic means with a very small quantum circuit and all, that at least is able to provide us an essence of quantum advantage. So what are the algorithms that we will be learning today? Mostly they are to illustrate the essence of quantum advantage with respect to its corresponding classical counterpart. But it may not be very significant in terms of very like fantastic speed up it is offering or great kind of an efficient system. I'm not claiming that. It is just to give you the essence. Okay, but this will be proven that it is best than the, or it is better than the best available in classical. So it's a kind of demonstration of quantum advantage. Okay. So for a better understanding, I will suggest, because it's a flow of continuous flow of like mathematics and all those things. So I'll be writing everything. I'll try to put everything so that for those who want to follow it, you can also just see it or go through it. But my suggestion will be, if you have a pen and a paper with you, available with you, just let us follow and let us just try to have the notes so that you will be doing every step. It will be having a create a better impact. That is what I can suggest. So our agenda is to demonstrate a sort of quantum advantage, right? What does it mean? It means that number of queries. So in terms of algorithm language, number of queries required for our quantum one should be strictly less than the number of queries required the classical counterpart. That is called the definition of quantum advantage is nothing but this. Okay, in terms of logic, it's ultimately the number of queries. Queries means, say, number of iterations you can call, or anything. At worst case, how many such combinations or how many such say steps that you need to follow. So either you call it steps or you call it like combinations or you call it queries, all of them are same thing. Okay. So say for this, we will assume, yes, I'm just writing everything. Say for example, state of quantum resistor state of quantum register, that is one thing that we will be taking, which is nothing but a linear combination. If I am able to change it, let me. So it is nothing but a linear combination of states. So unlike classical, in classical what we had only classical register, we have only one state. But here it is a linear combination of states where it is stored within a quantum register. So it's unlike classical register where we can store exactly one state at a time. If you're having any issue with understanding the handwriting and all, please let me know, because I'm writing it. Maybe there is some issue also. Second point, this is the first point, state of the quantum register. So right now, what I am doing right now is I am just trying to put together all the building blocks required to frame or to construct the quantum algorithm. What is the problem statement that we are solving for? Yet I have not told you that thing. I will tell that. But these are the basic thing or the common thing that you have to keep in your mind if you are about to frame a quantum algorithm. Okay. So state of quantum register, you have to think it of. Then quantum parallelism. Quantum parallelism in the sense, right now, if you have to devise or bring into picture quantum superposition, means all the possibilities will you can actually do at the same time. In terms of computing, it means, or with respect to the quantum algorithm, it means that computation of a function, any function it can be, for each of the states in the input register, you have to think it in now in this way. See, things are becoming little complex now. It is not that easy. What I am telling is, you have to frame or you have to think computation of a function for each states or for all say states in the quantum register. Why you have to do it on all stages? Because every advantage comes with a certain kind of a disadvantage. Similarly, here also, say for example, just I told you the Grover case, the amplitude amplification. Initially, whatever I want to do, I have to do with all the robots. Even if you see it, maybe you may be like right now that, okay, I have a super state, but I do not want to do a certain operation on the qubit state, say 4 and 5. Instead on remaining, I want to do that. You cannot do anything like that. You cannot really do anything like that. Whatever you want to do, you have to do it with respect to all the states possible. Okay. Yes. Yes. So that is a challenge. So if it is a say class operation, it means, say for example, I have 1, 2, 3, 4. It is not the way you can encode in quantum, but just for an example, say if the function is if 1 is nothing but the function is the addition function, maybe addition by say 2. For example, I'm just telling. So you have to do it on all. So your 1 need will be 2, 3, 5. Sorry, 6. Then what it is? 4 plus 2. Yeah. So all these things just plus 2. It will be 3, 4, 5, 6, 7. Likewise, it will be. Now the third point is a oracle. So maybe in last class only we were discussing about oracle. So oracle is nothing but a kind of a black box. It has a certain input, it has certain output. Or it can have say more input and more output as well. Okay, but it has a certain feature. That is, let me write. Oracle means it is a black box. Okay, sorry. Yes. So it's a kind of a black box computation, which is similar to a classical subroutine. No. Yes, someone asked a question that there we have done a certain kind of a phase inversion with respect to the target state. So that is nothing yet quantumly you have done doing. That is not yet quantum. Okay. So phase inversion also means, say for example, you have to, there is a lot of other factors as well. So it's just the way maybe you have applied a certain logic which only is effective for that particular say cell or that particular value where your phase inversion will be applied. For maybe all the other cases, it will be ultimately zero. So similar, there is a logic. It's not directly like that. So it's kind of, if I want to tell you, if I just want to tell you in very easy example, the phase inversion logic, it is say 0, 0, 0, 1, 1, 0 and 1, 1 initially we had. So, and maybe this is the value where we want to do a certain kind of phase inversion. Say for example, this is the value where we want to do phase inversion. So what we will be doing is, first we will check individually. I'm just telling you the classical logic. We have to check individually all the values. Then wherever I'm getting say 0, I will be making it 1. So here it will be 1, it will be 1, it will be, see here also it is 1. So I will make it 0 and this one also say 0. Now that is a phase flip on all the values. And here for this one, wherever is the 0, say I have done, make it, say, let me keep it unchanged or say maybe, yes. So this cell I can actually keep it unchanged. Say I'm just defining the logic. So what does it mean? On first qubit, I have applied a NOT gate, Q1, and Q2 is nothing. Of course, I can do this kind of operations. So right now it will be 0, 1, and 0, 1, something like that. Now you see, can I now tell that, okay, so please do a phase inversion, say for example, where it is a C phase, oh, sorry, say for community. Say for example, a control phase I'm now applying. Control phase means whenever this is 1, its phase will be inverted. Right now, so, right? So it will now become -1 and all the other values will be nothing but 0, because even if control is 1, if target is 0, then nothing will happen, no phase inversion happen. I'm not telling for C naught, I'm telling for C phase, right? So see, every operation is taking place on all the qubits based on our logic. So that logic is basically the function, but it has to be applied because of the quantum parallelism on all of them. So it's 1, 0, 1 minus 1, then 0, 0, then 0, 1. So if you see from this point, it is now, say 1, 0, okay, plus of minus, which is nothing but say minus 1, 1, plus 0, 0, plus 0, 1. So just see here, the phase inversion has already happened. But there is again a challenge. How I can identify that whether right now it's for 3, right? If you check it, it is for 3. We are able to make the phase inversion with respect to one of the states while it was in superposition. Yet in this point also, it is currently also in superposition. But the thing is that it is with respect to this particular state, which is 3, but what was my desired state, where I wanted to my phase inversion to take place, that was 1. Decimal value of 0 and 1 is 1. So how to do that? That comes if you just again redo all the operations. Whatever you have done, instead of the C phase, just keep on applying them again. Again, the same thing if you apply, you will ultimately go back in this stage. After a certain case, the same thing, same gate if you apply again. Okay. So it was 1, 0, sorry. It was 1, 0, yes. Okay, so that means after this, after Q2 is the second operation, third operation was a C phase on say Q1 and Q2. And fourth one is again, if I apply a X on Q1. See the how in different time instances, how beautifully the quantum states are being like evolving. That is the beauty of quantum, but that is a challenge of quantum as well. But after this stage, if I only do x of q1, then of course there will be no phase change or any phase. It will not affect the phase even. The x or c not get. It will not affect the phase. So right now it will become what? The first qubit, this is first qubit, this is first qubit, this is first qubit, and this one is the first qubit. So again, it will now be inverted. So it will become now 0, 0. Minus will be as it is, no change. So this will become now 0, 1. This will become, say, 1, 0, and this will become 1, 1. Check it. It is in superposition. Yes. Is there any phase inversion? Yes. Is the phase inversion like correct with respect to the state where it should be? Yes. So this is quantum parallelism and how with respect to a particular oracle you can actually work. Right. Just an example. Grover is like a lot more than this, but this is just how your any of your like phase inversion logic, or which is also known, this logic is also known as a diffusion operator. This operator, it's called diffusion operator. So this diffusion operator of Grover works like. Okay, so where we were, like we described the state of quantum register, then quantum parallelism followed by oracle. Oracle we was discussing. Just a minute to remove it. Right. Okay. Okay. Thank you. So now the thing is that measurement. This one is extremely crucial. As I was telling, it is to extract, not to obtain. There is a difference between obtain and extra. Obtain is whatever I am getting, and extract means I am just extracting, means certain logic that I am applying. So to extract the required result. Okay, that is measurement. And always remember that we need an input register. Different functions, not really, but the same function, but you have to tune it in the way, or you have to generalize it. If you cannot do that, you cannot apply quantum. You have to think of a certain generalization so that it applied on all the qubits. Still, your required one only has the reflection of the of your requirement. So whatever your requirement is, that will be reflected in only one step, not on the all steps. That has to be your logic. That function you have to define, so that it will be in superposition, but other will not be affected, or somehow effect will be nullified, or it will not impact. If I do not, maybe I have certain gibberish in one of the quantum registers because of all these things, but that quantum register I will not be taking into consideration while I'll be measuring it. I will ignore that qubit content altogether. I'll be focusing on other qubit content. So that gibberish will not come into picture. Maybe that holds certain other set of values, which was a temporary result. So it is your way of encoding the generalized superposed state on which you want to apply your oracle. So what I was telling, so it has an input register as well as a target register. Okay. Target register is where your output will be stored ultimately. Your output will be stored. So with respect to oracle, firstly, it is just like a readout. Readout happens in normal classical systems also. So even though our output is a linear combination of results, as per and it is equal as per it is like for a linear combination of inputs. So that is kind of a readout. As results can be random, so you have to define that how you want to get your desired result, or what form you want to have your desired result. Okay, so it's like that. It's like that. Say for example, often this kind of picture you will be seeing maybe. So this is x and this is y and this is x and this is say y XOR f of x. So here, if you see, in this stage through oracle, there is a kind of an entanglement between these two qubits. Why? Because y value itself, whatever is coming from the input of the target, it is somewhere entangled with respect to your outcome that you are getting from the another qubit. So there is a certain kind of a relation between them. So here also you can see an effect of entanglement. Okay. And generally oracle is defined as UF. U is for unitary and F is the function. Or often it's also represented like U or any way, or normal simple U, whatever you call it. Or say U of Fx. So all these things are equivalent. Okay, okay, let me use other color. Maybe this one. Okay. So now we'll start with the first algorithm, which is Deutsch algorithm, or you can say it, call it Deutsch algorithm, whatever you want to call it. This is the first algorithm to demonstrate quantum advantage. Okay, it has a certain input, which is 1 qubit. It can be 0 or 1, and has certain output, which is again 1 qubit, 0 or 1, anything. And the function is the function that I want to encode here. There is some issue with the black color, I guess. Or it is, what is happening here? Okay. Okay. So my function that I want to encode here is either a balanced function. I want to check whether a function is balanced or constant. So if a function is constant or balanced. For that, we need to know the definition of a constant function and a balanced function. Since I have only 1 qubit or 1 bit, whatever you say. So it's for F0 and F1. These are the two values that we want to check. So if, say, F0 is equals to F1 is equals to 0 or 1, anything. Like both are having the same value for f of 0 or f of 1. If that is the thing, then this function is called a constant function. And if say your f0 is equals to 0, your f1 is equals to 1, or your f0 is equals to 1 and your f1 is equals to 0, in these cases, we will call it a balanced function. Okay. Now, its claim is that classical computation requires 2 queries. Why 2 queries? Very simple. See, for classical, it takes only 2 queries. Why 2? If you want to say that whether f is balanced or constant, how many minimum number of queries you did? Let us check. So first you will be calculating f0. If you get a 0, it's okay. And if for f1 also, then you will calculate. So calculating f0 is query number 1. Then calculating f1 is second query. And if you get the same value, say 0, we will call it a constant function. If you get the f1 value to be 1, you will be calling it a balanced function. So for classical, in best case, you need 2 number of queries. The claim with quantum is that in quantum, you can actually do the computation with respect to only 1 query. So that is the claim of quantum. Now we will see that whether that claim is correct or not. We can devise to that output or not. That we want to check. Okay. Now please do full focus here. I'm using black color only instead of like frequently changing colors. I hope black is visible to all of you. Black color is good. Okay, thank you. So what we have to calculate is we have to imagine that the function we are calculating is in black box. Function under calculation is in a black box. Okay. So in classical methods, we know why it's 2 queries. So in quantum, the black box or the quantum circuit will look something like this. Say UF, I have told you, this is a unitary operator. This is a oracle. it will be having certain kind of an input register where input values will be given just in order to process or in order to help in the computation. There will be another register called the target register where your finally the output or the transformation will be finally stored. Okay. So initially it will be your ket 0 and we will start with the ket 1. How to build ket 1 and all those things, I hope right now we all know. And we will put both to a header mod gate and put it as an input. This is also a header mod and input. So after input at this instance, it will be say ket x, ket y. So why this is not 0 and 1? Of course, after header mod, it has become something else. So it has become ket 0 plus ket 1 by root 2. We all know now why. And ket 0 minus ket 1 by root over of 2. And here at output, we'll be getting two things. First is a ket x, which is unchanged value. Whatever you are getting, we'll be having the same thing. And here you will be having, say, y XOR fx. Now I am applying another header mod only on the first qubit. Okay. And then try to measure it. And this symbol is a addition modulo 2 or a XOR, whatever you called it. Or say XOR exclusive or. Okay. So your this 0 is the input register, this is input register, this is a 1 is a target register. And therefore, Oracle UF is to calculate your f of x. Okay. And so Oracle input is, Oracle has two inputs. Oracle input to quantum circuit is 0 and 1, but Oracle input is ket x and ket y. So UF, which is a unitary function for Oracle, works in this way. X product y, this is Oracle input, will be mapped to x product y XOR fx. Just first learn that how this different kind of encoding thing works. You should be able to at least identify that what is the meaning of this thing. Okay. I hope you were able to. If you are having any difficulty in the flow, please let me know. So your input register is, input register was what? Input register X was ket 0 plus ket 1 by root over of 2, and your output register, another input register Y, which is also called target, that was ket 0 minus of ket 1 whole over root 2. Right? Now we will be putting the values in the like Oracle equation that we have over here and see how the evolution takes place. Okay. So what was my UF? Let me again write the UF. So UF was X product Y is equals to X product Y XOR fx. So let me write the value now of X and Y. So it will be ket 0 plus ket 1 by root over of 2 product Y is ket 0 minus ket 1 by root over of 2 XOR f of x. Okay. Now, if I expand the input, say expanding the input, expand, U is this unitary operator itself. The unitary operator works in this way, which has this input and this out. Okay. So expanding the like input in 2-qubit form, it means what? Basically, the input to Oracle, this thing, the input to Oracle, input of Oracle, this is nothing but say 1 by root 2, okay, let me write 1 by root 2 ket 0 plus ket 1 by root of, ket 0 plus ket 1 product ket 0 minus ket 1 by root 2, which is nothing but half, then 0 0, I'm writing together 0 0 plus 1 0 minus 0 1 minus 1 1. I hope it's just simple the way we do the product. It is in the 2-qubit form where this is X and this is Y. Why I'm writing in this way, we'll just understand. From the subsequent step, we'll understand that why the previous step is kind of designed or framed in that way. This is your x and this is your y. Don't forget all those things. This is your x and this is your y. This is the input to Oracle in 2-qubit form, right? Now we have this thing. So this meaning and this meaning is exactly the same. Okay. Now we will be having the effect of these x product y XOR effect f of x. That we will be doing. Let me expand the line. So on Oracle, how it will work like, it will make half as it is. So your x will be x. I'm not doing anything with the x. And now you have your y XOR f of x. So what is y? 0, right? So it will be 0 XOR f of x. What was your x? That is 0. So f of 0. Any doubt, please let me know. Plus, this plus is here also plus. Now again x. What is your x now? 1. So 1 comma y means 0 XOR f of x means f of 1. Minus, similarly I'm writing 0 comma 1 XOR f of x, which is 0. And similarly here it's 1 comma 1 XOR f of 1. Bracket close. I hope now, with respect to the Oracle logic and with respect to f of x, we have expanded it, because x should be unchanged and y now will become y XOR f of x. Till this part it is okay? Till this part, the expansion and all? Okay. Okay, thank you. Now, what will happen for if I just take anything, f0, f1, f2, say p. So p XOR 0. So XOR of like anything with 0 will only be that variable itself. So a XOR 0 is a, and a XOR 1 is basically a bar. So that is a very simple thing. I'm not writing it. So, or even if I write, so 0 XOR anything, say p is anything, p anything it can be. So 0 XOR anything is basically anything, and 1 XOR anything is basically the complement of that. So if I just put the logic here, what it will become? Let me just write it. So it will now become half k0. This will be nothing but f of 0. And this is 1 comma f of 1 minus 0 comma f0 bar minus 1 comma f1 bar. Till this part, there should not be any problem. So this is the generalized expression. Okay. Now let me just once again write the generalized expression. Then let me try, like, start from that. So it is something like this. Say k0 f of 0 plus 1 comma f of 0 minus 0 comma f0 bar minus 1 comma f, I guess what it was, f1 bar. I'm just writing it correct. Let me check again what it was. 0 f0 1 f1 0 f0 bar 1 f1 bar. 0 f0 1 f1. Okay, it was 1 f1. Sorry. Yes, 0 f0 bar and 1 comma f0 bar. Now say the function is a constant function. Say, for example, the function is constant function. What does it mean? Whatever be my f0, whether 0 or 1, and whatever be my f1, whether 0 and 1, they has to be equal. That is the definition of a constant function. So if that means f0 and f1, they will be equal. So from this line, can I directly write that this thing says 0 comma f0 plus 1 comma f of 0 minus 0 comma f0 bar, everything in terms of f0 I'm writing. 1 comma f0 bar. Can I just write it? We can. So this is after a certain, like, taking common and all those things. So it will be like k0 plus k1 and whole thing with f0. And then this is like minus k0 plus k1. So, okay. k0 plus k1 and f0 bar. It will happen simple algebraic, like taking common and all. So it's half times ket 0 plus ket 1 into your f0 minus f0 bar. Okay. Now since your f0 and f1 can take anything, f0 and f1 can take either 0 or 1, anything. And here also, say for example, so whatever you write it, if you write f0 to be 0, so it will be 0 minus 1, because f0 1 will be then 1. And if you write f0 as 1, then it will be 1 minus 0, so it will be 1 minus 0. Now just check it once, that here in this example, in this equation, it will be either a plus 0 minus 1 within bracket or a minus within bracket 0 minus 1. That is a plus minus. Then this entire thing half into ket 0 plus ket 1 times ket 0 minus ket 1. Right? 0 minus 1 and 1 minus 0 differs by only a phase factor of minus 1. Okay. So ignoring the phase, because here the global phase, so here ignoring the global phase, as it has no effect on these kind of like output of the quantum measurement. So it will be ket 0 plus ket 1. Let me put the half over here. And this will be ket 0 minus of ket 1. Now, can I write it in this way? The half, let me just put it a root 2 and just multiply it or just apply it on both of them, like ket 0 plus ket 1 by root over of 2 into ket 0 minus ket 1 by root over of 2. Can we do that? Definitely, because root 2 and root 2 whole square is only 2. So we can do that. So after all these steps, wherever we have started from this thing. Okay, so ultimately we at this time we are in a position where we have values like that. Okay, so here it contains now ket 0 plus ket 1 by root 2, and this one after a lot of like thing had happened, ket 0 minus ket 1 by root 2. Right? Now let me go back. So this is the step. Now if I apply, now see what I'm doing next. I'm applying a Hadamard on the first qubit. Right? That is why from this I have written it in this way, like the first qubit and the second qubit form, nothing only for that thing. So now what I'm doing is I'm applying Hadamard on this particular thing. Hadamard. Now Hadamard on ket 0 plus ket 1 by root 2 is nothing but 1 and 1. So Hadamard matrix on the superposition will give what? We have seen this thing. So Hadamard on ket 0, yes, 0. So it will be nothing but 0. And this part we are not doing anything. So it will be root over of 2. But this is a state that we are getting or obtaining. Okay. So the first register will be having a value 0. So what was my observation? That is the first register after Oracle and Hadamard should contain the value 0. Right? Now say the function f is balanced. Constant we have taken. Now we have to take this is balanced. So what is balanced? What do we mean by balanced? Balanced means either f0 equal to 0, f1 equals to 1, and or f0 equals to 1 and f1 is equals to 0. Okay. So what was my equation? Equation means this equation I'm referring, the general one, this thing. We have to start with this thing, right? We have to start with this thing. So it was just in order to get it. See what logic we will be applying, it is on us. No one has any control on it. So why we have taken one on the target and not both the values 0? Because that is how we have to devise the algorithm. See, that is how this algorithm works. The quantum gates are your choices of operations. And in order to make it in this way, you have to think. You have to think that what should be the correct set of quantum operations and its corresponding order, and on which qubit you should be applying them. These are not at all easy, or at all easy. Like devising a quantum algorithm is very difficult. See, we are just here learning or going through a established quantum algorithm. But think about, you have to devise it. Isn't it really very difficult to think it in this way? That is why there is very less number of discoveries and research work that like happen in the like core or the fundamental level for the quantum algorithms. There are very few quantum algorithms that you will be having. They are like mainly these Dewey algorithm, then Dewey Jobs algorithm, Bernstein, Vazirani, Simon, Grover, Shor, HHN. These are the fundamental algorithms. And whatever you want to learn, you have to first know these algorithms. Then maybe some part of it, if you're able to work, then maybe that will work. Okay. So that will be some algorithm. But these are very novel quantum algorithms. Those were devised. Okay. So where we were initially, that is a big equation. It was something like half. Okay, just also one more thing notice here. So F0 and F1, they are in complement, right? So F0 is nothing but F1 bar, and your F1, vice versa, F1 is nothing but your F0 bar. Also, just from the values, I'm just writing it, nothing else. So whatever we have written here, it means F0 is equals to F1 bar and F1 equal to F0 bar. So from the equation, if in places of the F0 bar and F1 bar, if I just replace it with F0 and F1, just see it over here, in place of F0 bar and F1 bar, if I replace it with F1 and F0, then what it becomes? 0 F0, 1 F1, 0 F1 and 1 F0. Right? Simple. The same thing I'm just writing. So it will now become half K0 F0 plus 1 F1. It was minus 0 F0 bar, which is now F1. And this is 1, and it was F1 bar, which is F0. We can write it down in this form. Okay. So now just taking some F0, F1 common and all those things, after a certain step, we will be getting this thing. I'm not writing there. So you'll be getting it like K0 minus K1 and F0 minus this thing. Okay, let me write. Let me not do any like step jump. Just a minute. Oh, what is the issue with this thing? Yes. Let me write. At least for one algorithm, let me write everything. So here I was. So it's basically what I am doing is F0 I'm taking as common. So it will be K0 minus K1 times F0 plus it will be K1, if you check it, minus K0 times F1. So making it minus and all, so it will be half K0 minus K1 F0. Let me put it as it is, minus K0 minus K1 times F1. Now, in place of F1, can I write F0 bar? Yes, I can write. Why? Because F1 is nothing but F0 bar. How? Because it is a balanced function. That was our assumption. So from here, I can write it down that half K0 minus K1, and this thing, if I take this as common, it will be F0 minus F0 bar. Okay. Now, similarly, F0 and F0 bar can be either 0 minus 1 or 1 minus 0, taking the global phase out and all those things. Can I just write it in this way? Can I just write it is ignoring the global phase, ignoring the global phase. Can I write in this form? That is because F0 and F0 bar is nothing but either 0 minus 1 or 1 minus. So from that logic, I'm just writing that it is basically half then ket0 minus ket1, and this one also, the f0 minus f0 bar will also be ket0 minus ket1, ignoring the global factor. So it will now be 0 minus 1 by root 2. Again, for the same algorithm purpose, tensor product ket0 minus ket1 whole by root 2. Now this is the first qubit, and first qubit after all these evolution, time evolution, and this is the second qubit status. I'm not doing anything with the second qubit, so these I am keeping unchanged. So ket0 minus ket1 by root. But first qubit, I am applying a Hadamard. Just see the circuit. I have applied a Hadamard. So on Hadamard, if it is applied on ket0 minus ket1 by root 2, it's reversible. So it's basically ket1. Absolutely. Okay. So now have you just seen it that if you devise this quantum circuit, and after all the operations, if you measure in a single query, if you want to measure whether the function is a constant function or a balanced function, you can do that by checking just the content present in the first qubit. So from this, what you can conclude? You can conclude that if the function is, say, constant, your first register content will be what? It will be ket0. And if the function is balanced, then your first register should give you output 1. How many queries you are making over here? Only one query. Therefore, what you can see over here, you can see a quantum advantage. But this is not really very advantageous for us to do in this way. But still, for quantum, it is very easy because we are again simulating how it works in quantumly. We have to do all these calculations and all. So this is the essence of quantum advantage. The same problem you can do with a lesser number of queries. Is it okay for everyone? Of course, I'll be keeping everything. Is it okay for everyone? Great. So we have 10 more minutes. And so what we can do is, at least we can have a base ready for the second problem that we will be watching. So what is the problem we will be understanding, which is kind of the same thing, Deutsch algorithm, a little bit of extension of Deutsch algorithm. We will watch that, understand the problem statement for the extended problem. Also, we will see that what is the number of queries or kind of a complexity of the problem, extended problem with respect to a classical computing. We'll look into that. Okay. So for that, yeah, number of is good enough. So I could have given a break, but because it's only 10 minutes remaining, so I recommend the book. There is a book for quantum circuits only. See, one paper I can refer. It is a thesis paper by Lovett. So Lovett. Okay, so you can actually refer his thesis work. It was basically related to quantum work, but instead of that, you don't need to focus on those areas. But the initial few chapters of those thesis, if you go through, it's very easily written, and you will be understanding. We're starting from all the principles and all. Yes, so it is Lovett. Okay, just Lovett. Is the importance of conditional choosing? What questions you have written? Let me stop and just take one question. Mm, 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 mm. What is the importance of conditions choosing constant? Conditions means, what do you mean by conditions? Choosing constant and balanced condition. What is the importance of conditions? Choosing constant and balanced condition. I mean, just elaborate what you want to ask. What do you mean by conditions? I just want to know that. A.K. Jha. Let me meanwhile just write. It's love it. Love it. This is okay. I'm not repeating what you are having doubt. Maybe you are muted or something. Just try to write it. Okay, ignore, ignore. Yes, love it. Just check in the chat. I have written LOVET. Okay, let me just do the remaining thing, which is for Deutsch algorithm. So for that, let me start it from the current slide. Yes, yes. So in Deutsch algorithm, we have seen for only one single input. It can be whether we are checking that whether it is a 0 or a 1. So based on the function, whether f0 and f1 with respect to that bit value, whether it's like same or not. If it is same, we are calling it a constant one. If it is different, we are calling it a balanced. But just imagine we have, instead of a 1 qubit input, we have a n qubit input, or multiple, like more number of qubits that we have, 2, 3, 4, 5, 6, 7, anything that is more than 1. Now, how we can define the constant and the balanced one? Constant is very easy. That is all the values, like function at every point, the value should be 0. If that is the case, we will call it a constant function. But how to define the balanced function? If half of the inputs will give me 0, then half should give me 1. But here, remember, we are not questioning that which inputs are giving 0 and which inputs are giving 1. That is not the problem statement. And we should not be doing any manipulation with the problem statement itself, ever. So the problem is whether the entire function is for any input, whether it's a constant or a balanced one. So depending on the number of similarity or similar input, we will say whether it's a balanced one or it's a constant. For constant, if it is all 0, or all 1, we will call it a constant one. If it is not, then we will call that, if it is like half number of zeros and half number of ones, then we will call it a balanced function. That is the thing. And also here, one more thing we have to consider, that the function can be either balanced or constant. It cannot be like nothing of them. So we have to assume that it's a exhaustive space. Okay, so it's like if it is not constant, then you can directly say in that number of query that okay, it is a balanced one. So that you can check it. Okay, let us start. Let us start with defining it. Then quantum part we will do tomorrow. So it's an extension of Deutsch algorithm. वो वाला ग्रोवर था, ये वाला Deutsch algorithm है. Both are very different. One who are asking that here it's like 2 queries, and वहां पे हमने देखा था कि एक quadratic speed up था. For that was a Grover algorithm, and it is Deutsch algorithm. Here we are not doing anything. Here in just a number of queries. See, big O of order of n is order does not mean the exact value of it. I hope like asymptotic notation, if you are well aware of it. So order of means a class of complexity that you refer to. So order of n means it belongs to n. Order of, say, order of log n means it's a function of log n. But it has a lot of other constants, a lot of other factors there. So here it is in terms of a numeric queries, how many basic level, how many queries we are making. So in classical, we had to give like 2 queries. In quantum, we have to give like 1 query. It has nothing to do with the like Grover's algorithm and all. That's completely different. Okay. So this is Deutsch algorithm. Thank you. Thank you. So it is a kind of an extension of the basic Deutsch algorithm. Let me just define the problem statement where we believe that instead of, okay, let me write in like black color. So instead of 1 qubit input, here we assume we take n qubit input. Okay, so the function will now look like, say, 0, 1 product, tensor product n times. Okay, this means what? This means very easy. 0, 1, say a case of 2. It means 0, 1 product 0, 1, which is nothing but, say, 0, 0, 0, 1, 1, 0, 1, 1. So a 2 qubit system. So 2 qubit system, you write it in this way or in this way. It's same. Similarly, in qubit system, I'm writing in this way. 0, 1 tensor product n will be mapped to 0 and 1. Okay. So this is a single qubit output. So the function is either balanced or either say constant. That is all values uh, corresponding f, say f of values, let me write, are same. That is constant. Or it can be function is balanced. Balanced. It means what? That half of the inputs will give 0 and half should give 1. Okay, but also I'm just writing, we are not calculating which input. Okay, so this is the function definition. Let me stop here, I guess. So tomorrow we will start exactly from this definition. Okay. Okay. Thank you. Thank you all. We'll see all tomorrow. Thank you, everyone.